Before we will start out with zfit, since we talked yesterday about TensorFlow, to give the completion, we're going to now talk a little bit about very shortly about the statistical inference that we can basically do with TensorFlow. So basically what is already there. And TensorFlow itself doesn't, it's optimized on neural networks, but there is a package which is called Tensorflow Probability. And this does probability computations in a more general sense and contain things that are already quite similar to zfit. Most notably, the distribution package. With the distribution package, we can do something like create a Gaussian function or a normal one, and then we have basically a PDF here. We can sample from this distribution and we can get a probability out. So this is now a normalized PDF, which already sounds very similar to what zfit does. They can also do more. We can have mixtures, for example, of different PDFs, for example, of the Gaussian we created before, or of the normal distribution. Or it even offers to have joint distributions with joint probabilities. So this all looks a little bit like, okay, can we do just model fitting with that? And we've sticked quite close to what they can already do. But zfit has a larger approach, and there are a few things that are not possible there. So most notably, the whole TensorFlow probability builds on analytic functions. So everything that is analytic, sampling is analytic, integration, everything is basically analytic. While zfit has a way more general approach and implements many numerical algorithms for sampling and integration, for example. Plus, it also takes care of things that are common, like different normalization ranges and such, which TensorFlow Probability do not really have as a concept. So TensorFlow Probability is really like a statistics library, which is great also to build a model or something, while zfit is a more model-fitting specialized library. They work together quite well, so you can also build your model if you want inside TensorFlow Probability, and you're more than welcome to do because they have a lot of distributions. And then there's a very simple wrapper in zfit so that you can use it fully compatible with zfit. Actually, inside zfit, some PDFs are just wrapped from TensorFlow Probability. So going now to zfit itself. As I mentioned before, these are the 5 parts of zfit, and we will in this extended introduction basically go through all of these parts, and you'll see a little bit the possibilities. The data object in the beginning is just here to have a common frame for the data, but there is not a lot of pre-processing capability. You can apply some simple limits and such, but in general, this should just be delegated to another library such as a pandas data frame. So the idea is you can load it from root, you can even load it to zfit and then convert it to pandas, then from pandas do your pre-processing, convert it back to zfit. Compared to other libraries, this is also not necessary since we have pandas around, so why reinvent the wheel here? And what we have here is a space object. So currently zfit makes, maybe also compared to other libraries, a strong distinction between what is actually a parameter and what is something that is normalized over. And the space basically defines our data. So the data input, not the parameter itself. That's why we just get a range in there and have a name here. So we do in our first example, we just sample from a normal distribution. Also the notebook is, there's a lot of more stuff in there. So it's also meant that I'm not going through all the methods of the objects, but here's really the explanation for these objects. You can play around if you're interested with them. So when we can load this here into the data, so into zfit data object. And if you have this, we can see how many events we have and get our data. Since we applied the range here, the data object applies this rectangular cut to the space we defined here. That's why we don't have 10,000 here anymore, but we lost the tits, which is what we usually want. It also has an NOPS, which means the dimensionality, it's one-dimensional. The model itself is the most extensive part. So we will look at that also in a separate, in other tutorials more. In short, it's a PDF that is normalized and it's parameterized by parameters. We see here how parameters build. We can have an initial name, which is a unique identifier. We cannot have two parameters named the same name because it doesn't really make sense. If you minimize something and you get the value of mu is 5, then which mu? So we have to have a unique identifier here. We have an initial value and we have limits if we want. We can also specify the step size as a guessing, and we can also set it to floating or not. If you're just omitting the limits, it's still floating. And this is also an attribute that we can just change, setting it from floating to true. So to create a Gaussian, we specify the observable, we specify what are the parameters, and we got our object. The Gaussian also has a dimensionality, or a PDF has a dimensionality in which observable is defined, what's like a default space it's in. This is used, for example, for default sampling limits, and the normalization range. The normalization range, we didn't specify that explicitly here. We could set it, but this is just the observable space that was already defined by default, but it doesn't have to be. The normalization range is the range over which the PDF is normalized to 1. And we also have the parameters here with the name, which is the name of the PDF. So every Gauss PDF that we create has a params dictionary, and this contains a mu and a sigma. But the parameters itself, they can be different. So we see also the parameter above that we create is sigma 42. So that's why the parameter that is assigned to the sigma, so the value in the function itself, is this parameter. But we can also we can use the same or something. There's another way to retrieve the parameter. So this is if you want to know what's the mu of this function, what's the sigma of this function. But often we're just interested to get all the parameters out because the Gaussian is simple, but we have maybe more complicated models, and that's why there comes the get params function in there. Get params just recursively can extract all the parameters that are floating automatically. There are 3 arguments, but if you just want to have all the 3 parameters of a model, then get params is your friend, and it automatically extracts independent parameters, goes down in models like sums and so on. We can also see the difference between the two. If you now create a Gaussian here as an example, where we use mu as the parameter for sigma and mu, then if we look at the params attribute, this is still the same because the mu of our Gaussian is the mu and the sigma of our Gaussian is this parameter, which is also the mu. But if we now say the get params, if we call the get params, this will just return us this one parameter. It's just a collection of the dependent parameters, and we just have one independent parameter here, so it just returns this one. The functionality of a model provides 3 basic main functions, which is on one hand the integral. This is normalized over the default norm range. We could also specify this here. And as we've seen in the tutorial before, this just returns a tensor, but again, just calling square root or something on that, we don't care a lot, gives us a value again. Sample creates us a sample. It's a data object again in zfit, so that it can directly be used with other things, but we can always do this unstack x thing, and then what we get is just the values that we sampled. And the sample, as mentioned, is a data object, so it has again in which observable this was sampled, what's the dimensionality and such. Or we can just feed that basically back into the PDF and get the probabilities out of it. You see, this looks also quite similar to the Tensorflow Probability model itself. And we've seen so far models, and the crucial aspect of doing any kind of fits, of course, is to do some plotting. Again, this is not functionality of zfit, so we need to use matplotlib, for example, or any of your favorite library, but it's pretty simple. You can get the lower and upper bound, for example, from the data range like this, you just create some X, you evaluate this X in the PDF, and you just scale by number of bins, and then the whole size. It's just a rescaling factor. You will see if you get that right or not. And then you can just plot these things. We can, of course, have nicer plots, and there's also, if you're interested to write nice plots functions, this is stuff that can be contributed to zfit physics, which means plotters, writing a good plotter is very hard. So writing that stable, it's an impossible task. But since it's often used, the idea is to build some functions that can be used by physicists, which are maybe less stable, but they work. So this is stuff that could be contributed to zfit physics. We used the Gaussian so far, but zfit contains a few more models. You see the wrap distribution here. This is to wrap any kind of Tensorflow probability distribution. So here we do not just have these functions, but anything defining Tensorflow probability as well, we can have here basically as well. But most notably are polynomials. We have a KDE, we have a sum, crystal ball, yeah. So now we're going to build a slightly more complicated model, because with the Gaussian we don't do a lot in physics. Therefore we define a new observables. We wouldn't need to, but let's make it. And create our signal, which is now a crystal ball function. We create the combinatorial background, which is an exponential. And we create a partial reconstructed background. So we're going to now make a model that incorporates 3 parts. On one hand, the signal that we expect to be a peak. On the other hand, the combinatorial background that is an exponential. And on the third part, we have partial reconstructed background, which is just some difficult shape, basically, that leaks in our signal region, and that we approximate with a KDE from Monte Carlo. So what we do here is we can just create an ad hoc Monte Carlo simulation. Let's say this is data, we can say this could be some Monte Carlo simulation. And then we create our Gaussian KDE here with an adaptive bandwidth. This is currently version 1, it's getting improved. Now we have these 3 components. And now we can compose these models with the sum. The sum here takes, if you have 3 PDFs, it takes 2 fractions, because the last fraction is 1 minus the sum of the fractions. We can also give all the 3 fractions if you want. This is, again, let's say one of these features of zfit. If you give in 2, it's automatically normalized 1 minus stuff, and it all works out. In case you really want to have a special case, and for whatever reason you want to take over control of these fractions manually by hacking something, or I don't know what, you can do that. And you can provide the same number of fractions as there is PDFs, and then they're just used and not normalized, meaning now it's up to you to look for the normalization. You can do that, but of course at some point then certain control is relieved. What we can do is, if you have these parameters now, we can set a certain value of a parameter. Parameter or objects, they can have a value. And what we can do as well, it's to use a context manager, which means inside this context manager, the parameter has this value, outside it loses that again. Can be quite useful sometimes. Most notably now, because what we're going to do now to fit this model afterwards is to sample some data from it. Before we could just create with NumPy, but now we want to just use the model to sample from it since we already have it, and then fit that to the data. But of course, the fit is a little bit easy if we just use the same initial data as we sampled. So we're going to set the values here of these parameters to different values. Up here, what we have is the parameter.setValue, which sets the value for one parameter, but sometimes it's useful to set n parameters. So there is a function which sets multiple values here for multiple parameters. Inside this context manager with the different values, we use a sample to create a sample of 10,000 events. To have a look at, to see how that looks like, we got this here. Side note on the sampling, what I'm doing here is just one-time sampling. If you want to do toys and do repeated samplings, there's a more efficient method, as we will see afterwards. This is now the whole PDF, and it would be nice, of course, if we could just plot and see all of the components. Again, we're using Matplotlib, so it's entirely up to us. And this is as difficult as it is to plot the components, which means we're just iterating now through the PDF and through all the params. The params of the PDF are just the fractions. Remember here the difference: if you do get params, you will get all the free parameters, meaning also the parameters of the crystal ball and of the exponential, which we're not interested in. We're interested in here to get the parameterization of our sum, and the parameterization of our sum has now 3 parameters that just describe the fraction. So defining that, we can now plot the whole model and we see all the components. Very nice. Of course, this can now be extended, adding legends and such. So what we see here is exactly this fraction. We have signal frag, we have other frag. So we have just these parameters of the whole model now. Extended PDFs is sometimes we're interested in the shape of things. That's what we've done so far, building our models, but often we also want to count how many events are actually in the data and get the right uncertainties. Therefore, we can build an extended PDF and add a yield to it. One design philosophy of zfit is that we can build the yield either by using create an extended, which creates a copy and creates a new model, but sometimes the copy, because you can implement your own models, is not implemented or something, so you can always also set the yield in place. The important design decision is though that if you run some code and you have non-extended models in there, and now you extend them and you run the same code again, there is no change. So an extended model runs exactly the same as an unextended would. The only difference is that if we extend the model, we get some new options now that we can use as well, but it doesn't change the behavior. So one of the things that we can do is we can, for example, use now the get yield function and we get our yield. Or we can, instead of using PDF, we can now use ext PDF as seen here, which is the PDF multiplied by the yield. So the PDF function, whether it's extended or not, always gives the normalized probability. The ext PDF gives the normalized probability scaled by yield. And of course fails if the PDF is not extended. So what we can do is we can either now take our model from before and create an extended yield. What we're often more interested in is to know the yields of all the species before. So what we better do is we create a signal yield, a combinatorial background yield, and the part record yield. All our 3 parameters, create an extended signal, extended combinatorial background, and now we have 3 part record, and now we have 3 extended PDFs. And with those, we can build the sum. The sum now has a new feature. Before we needed all these fractions. Now, if every PDF is extended, we do not need the fractions, and the yields are automatically taken and normalized as fractions. Again, this is now an additional service that zfit does, basically. This doesn't change the behavior because before it was not possible to give in just 3 PDFs that are not extended. Furthermore, if we give in now, if we say, okay, yields, we want to have something different, we can still give in the fractions as before and all behaves as if it were not extended. After we build our model, we can turn to the loss, which combines the data and the model, plus some additional terms to the likelihood if we want them, like constraints. This is how we build an unbinned negative log likelihood. This is now with our simple Gaussian model. So we're using the simple model first to illustrate that. This is unextended. And we can just retrieve the value by calling that value. This value depends on the parameters of the Gauss. So if you now do parameter.setValue, this would change the value that we retrieve. This is the value of the negative log likelihood. The NLL, the loss itself, has also attributes. It knows which model and which data and which constraints that are in there and this can then be used by other libraries. It also has get params, which, similar to the models, just automatically and recursively extracts all the parameters that it depends on. Now, since we're interested in the signal events, we can create an extended unbinned log likelihood with our extended sum that we had above and the data object. And we see now also we have quite a few parameters that this whole thing depends on, which includes yields and shape parameters. Having built our loss, and we see these steps are all really independent. So if you look at that, building the extended loss, we're given a model and we're given a data. And this was the same if we used the Gauss and the data. So this is all, we can make our model very complicated. Doesn't matter, it's all the same steps. Also, if you now go to the minimization, we don't need to know anything about the previous steps. We can build here a minimizer. For example, Minuit. There are also other minimizers, but Minuit is by far the most reliable one. And what we're doing here is just using the internal numerical gradient, but we could also use the TensorFlow gradient. This depends. For smaller fits, sometimes the Minuit gradient is better. Plus, we can also specify the tolerance and such. Now, we could just minimize the whole loss and find the minimum. But sometimes we want to fit just certain parts first. Like a typical thing is the combinatorial background. As we've seen before, we do have this right tail for the exponential. So we see here we have this combinatorial background here. And if you want to fit our whole PDF, this can be a little bit hard. So it's maybe worth to just fit the right part of the exponential first, and then fix this parameter, and then fit the whole PDF. And how we would do that is, what we just do here is we create a data object with only the right tile. So we have we create a new space which defines our range in the same observable auto mass, but with different limits. Instead of 0 to 1000, we go from 700 to 1000 to just include events on the right side. We take our data and create a new data for the tail. We can also change the normalization range of our combinatorial background. We do not need to access here the parts inside our whole PDF. We just take the object we already created before. I mean, we have it laying around. We create here a loss just of the combinatorial background and the data that is just defined in a tail, and then we minimize that. There we go. So now we fitted our right tail to the data. Since this is now fitted, we can also just fix the parameter lambda and say it's not floating anymore. And now we can do our fit. The minimize takes two arguments currently, which is on one hand the loss that we want to minimize, and on the other hand, which parameters. If there is no parameter given, then it automatically just uses this getParams function, which automatically extracts all the free parameters. Free parameters meaning they're independent. We will see later on there are composed parameters, and the floating ones. We could also specify explicitly which to use, in which case it just uses the floating parameters that we're giving. So even if we give no lambda in explicitly here, it won't use it. But if we list here which params to use, then it will only use this subset and only the floating one of this subset. But usually we're interested to just minimize all of them. So we can just give it a try, run it, and then afterwards plot the model. This is the plot of the fitted model. Looks spot on. We get this information out. That's the typical I-minute information. And what we get here is the result. The result, again, is independent of the minimizer. The minimizer doesn't remember state in this sense. And now we're at the fit result. And the fit result itself stores all the information of this minimization process. We can just print it, for example, and it gives us a nice overview of what it is, what are the models and the data contained, and whether it's valid, and all these things. Plus, what are the parameters. We can also, an important part of the result is, of course, to look at the model, at the parameters. It has a params attribute, and it has this nice representation, which gives us the value where it's at limits. We can also add more information to that, as we will see. If you want to access, though, one of the parameters here, this may be important. We do not access it by its string identifier. So we do not put in now mu as a name, but we're putting in the object we had before. So really this mu parameter. And what we get out is a dictionary that contains all information about this parameter, which currently is only its value. The result itself also contains more information, like the function value at the minimum, whether it's converged, whether it's valid, and such. What we can do as well is to roughly make an estimate of the uncertainty using either the Hessian method or the minus method. These methods are, if you use the minute minimizer, currently they're using as the minute internal one, which is very good for validation. So you know you're using the official method and very fancy stuff. But there are also alternatives in NumPy and even error estimation, which are still a little bit newish and experimental. We're just testing them that they get the same results and try to get into the same speed. What we see here now, if you print again params, we get now not only the value and that limit, but we also get the result from the minute Hesse, which gives us an estimate for the uncertainty. Hessian uncertainty is just taking the second order matrix, so the Hessian matrix, inverting it and stuff, and giving us the approximate profile around the minimum. But we can also use the error methods like minus to produce really a profile that gives us then the upper and lower error result. We can print the errors that are returned, which we can use directly, or again, get our params, because now this information is additionally stored here in minute minus. Just to reduce a little bit on the computation time for the tutorial, I just use 3 parameters here, which means just the 3 parameters now have this attribute. What's maybe uncommon is that error also returns a new result. It can be that during the profiling with the new method that we provide from zfit, that a new minimum is found. In case this happens, so during the profiling, it realizes my old minimum was actually not the minimum, it will return here a new result of that minimum, and it will change the current result that we used, the flag. It has a flag which is called valid. It will change this flag to false, which means from that point on, it's not valid anymore. Which in the end is just what's the right way to do. It basically doesn't decide, but it gives it back to the physicist, whatever we plan to do with that. Maybe say we don't care, but it just gives us explicitly this information. We can do also statistics on our own, or doing some kind of error estimation that we want, which is, for example, doing a simple profile, just evaluating the loss at certain points of a certain parameter, for example, the signal yield, and then just assign that values, append this to the list, plot that here. What we also see here is that the set values method, this can also be used, that we've seen before, this cannot just be used to set it to specific values, but we can also say set all these values here, the get params, all the ones of the NLL, the independent ones, to, and instead of specifying a list here, we can also give a fit result. This means set all the params to what you get, to what they were in this fit result, which can sometimes come in quite handy. Furthermore, we can also access the covariance and all the thing. And now we're finished here with the set fit, as in the whole workflow. Meaning, in tutorial-wise, there are going to be 2-3 smaller tutorials, more explicit on certain parts now. And in terms of logical flow, this is the beginning of Hepstats. I didn't really talk before about Hepstats, and it's also not going to be the goal of the talk, but it's still contained in the tutorial because this makes it complete. as usual, we're not just interested in doing a fit, but now we want to know something. For example, we want to know a confidence interval of a certain parameter. And what we can do is just use hapstats. I'm not going into details, run it with all the stuff we created above, and it calculates for us all this interval estimation, does some nice plots, and so on. We see here, just the only thing to note maybe is that it uses directly the result from above and which minimizer you want to use. And that's it. That's all we need to give further back downstreams. And we see we get just this plot out without doing anything.